We're going to go back to a dark place, Brady. A very dark place. Place we haven't been to for about 10 years. We're going back to minus a 12th.
I'm going to give you an astounding result.
I know this looks like a bit of mathematical hocus pocus sort of thing, but actually, in truth, it's not. And I'll tell you why we know it's not. So we sort of told a story about the sum of the natural numbers. I'll start from 0. It doesn't really make much difference. Up to infinity, which, you know, 0 plus 1 plus 2 plus 3, all the way up to infinity. We sort of told people that this should be equal to minus a 12th. Okay?
Oh, the equal sign.
The equal sign. So, right, so this is you know, we upset a lot of people. Lots was said. Some of it was fair. Some of it was a load of rubbish. I don't want to go into too much detail about my feelings about that. But we created a bit of controversy, but we also got a lot of people interested in these sort of questions. So I think it was worth doing. Anyway, why have I decided to come back to this? Well, about maybe a year and a half ago, I saw a tweet which annoyed me so much, right? that it actually made me go scuttling away to sort of do a little calculation to sort of disprove the content of the tweet. I won't say who the tweet was by, and I did disprove the content of that tweet, but actually in doing so, it actually sparked a research program, which this week we are going to be putting a paper out about it, which we're really, really excited about. So I want to tell you a little bit about it. But I have to go back to this sum to sort of tell you. I'm not going to do it as we did it last time. We're going to do it in a slightly different way, a bit more of an intuitive way. Okay, when you do this sum, okay, how do you do it? Well, one thing that you will often do at you know, when you see a sum, an infinite sum, or an infinite series, if we're going to use the technical term, you know, you normally take the first bunch of them, right? So you take the first n of them. So I take this sum up to capital N, right? And I see what I get. Okay, so so I'm taking 0, plus 1, plus 2, plus 3, and I go all the way up to n, and I stop. And then the idea would be that you take this n to infinity to get back to the thing that you're after, right?
You say take it to infinity like that's a place you can go to.
Well, quite.
There's no finish line here.
Yeah, well, quite. We'll come back to that. Don't worry about that. I agree. People are too flippant about this. But let's talk in the language that I think people are familiar with. This idea that, you know, you've got an infinite sum. I'm just going to cut it off at some finite number of terms and then see what happens as I make that number of terms bigger and bigger. Okay, so this is what you would do for this sum, okay? I actually sometimes think people didn't realize that I knew that you could do this. Right? But anyway, okay, I do know this. And I know what the answer to this is, right? It's n plus 1 over 2. And, you know, this is well known and you know, goes back to classical times, I think.
And in this particular case, the bigger n gets, the further you go along this line, the bigger the number gets.
Clearly, right? I mean, you can see that you can check that this is roughly going to give you the right answer. If you just take if I stop it here, so I stop at n equals 2, answer I should get is 3. Okay, is that what I get? Yeah, I do. If I stop at the next one, I get the right answer. I keep getting the right answer. So this formula works. And of course, you're absolutely right. I want to then I want to remove the cutoff. I want to remove the regulator. This is the language I'll use for this. This n is like a cutoff. It's a regulator. As I remove it, I'm obviously just going to blow up. The answer I get is just going to be infinite, right? But actually, there's even something more alarming about this that I think is that there's no sign of minus a 12th here at all. There really isn't. It's not there. Okay. This is kind of weird, and it's unsettling for those minus a 12th sort of advocates like myself. You know, where is it? And actually, this was answered by Terence Tao, the famous mathematician, and he explained why the minus a 12th isn't appearing here and how we can make it appear. And it's to do with the fact that what you're doing here is really quite drastic. You're really cutting this off in a very sort of violent and sharp way. And you don't have to do that. So let me explain a little bit more about what I mean by that. So what am I really doing here when I do this, what's called a partial sum? What am I really doing? It's like I'm taking the original sum. I'm going to use the word sum rather than series because it's just a bit more familiar. This is the infinite sum, but I'm weighting each term. Okay? I'm going to add a weighting factor to each term. So this is what I'm really doing here. Let me explain what I mean by that. So it's like if I was doing this, then this would be 0 times some weighting factor, which is w of 0, whatever it is. And then this next one is 1 times some other weighting factor. And then 2 times some other weighting factor. Okay, and so on. And so you go all the way up to maybe the n minus 1th term. That's got another weighting factor. And then the nth term, it's got another weighting factor. And then you can carry on if you wanted. In fact, you do carry on, you do the whole thing. And basically you carry on, and each term in the sum, which is just 0, 1, 2, and so on, you add a weight, you weight it by a certain number. And what are you doing here? Basically what you're saying is all these weighting factors are 1.
When you do the drastic cut.
When you do a drastic cut, you're saying all these are 1.
Yeah.
This one's 1. But all these are 0. So you're saying the weighting factor is 1 until you get to the nth term, and after that, all the weighting factors are 0.
Right.
Okay, that's what you're really doing here. Okay, so what does that mean? That means this weighting function that you're multiplying each term by, it looks a little bit like this. This is a terrible drawing. It starts off at 1, okay, and then at around the point n, it very sharply turns to 0.
Yeah.
Okay?
Yeah.
That's exactly what you're doing here. Now, Terence Tao says the reason that you don't see minus a 12th is because of that sharp transition. He says, you don't have to do it like that. There are other ways to regulate this sum. Now, I'm not doing anything weird, no weird analytic continuation, anything like that. Terence Tao says there are other ways to regulate a sum. Don't do the sharp transition, do a smoother one. Something that takes you between 1 and 0 in a much smoother way. So it's just, something like this.
Yeah.
Okay, you could do that. And it's the same sort of idea. You're still regulating the sum. You can still move the transition point, to larger and larger values to get back to the thing that you're after. Okay, so what happens if you do that? Okay, so let's do an example. So another possible weighting function, which would have the property that it sort of went between 1 and 0 in a much smoother way, is e to the minus n over n. Okay, you can see that at this end it's 1, and at the far end it's 0. And then there's a kind of a transition point which is set by big N. It's going to be around here somewhere, and then I can move that along and remove the sort of regulator, remove the sort of way that you're sort of controlling the sum. Okay, so you can ask what you get if you use this, and you can do this. This is actually easy to do. If I calculate this, this is what I get. I can actually calculate this exactly. I get e to the 1 over n, e to the 1 over n minus 1 squared. So you can now see what does that look like? Well, you can plot it, and it looks a bit like this. So this guy just grows. Okay, so well, it looks infinite. Yeah, it is infinite. Okay, so all right, well, that's not very impressive, is it? I thought we were supposed to get minus the 12. Well, wait. Okay, now let's see what happens. Let's actually look at the behavior of this. We're using this nice smooth weighting function. Look at the behavior of this for very large n. And you can calculate this. And you find that for very large n, it goes like n squared to leading order. The first correction. Okay. And then everything else vanishes as n goes to infinity. So there are further corrections, but they're vanishingly small for infinitely large n. So you're going to say to me, well, you've still got infinity there, haven't you? Okay, the minus the 12th has appeared now. Okay, but you still got infinity. Actually, what does Tao tell us? Tao tells us that this is very, very general behavior. That if I take any smooth weighting function, okay, and we extended some of his results actually, and did a few more generalities. If you take any smooth weighting function which goes between 1 and 0, and if you go to 0 fast enough and you've got some transition point set by the end, if you do that, then you'll always get something which goes like c, some number times n squared, minus the 12 plus the small stuff. That becomes vanishingly small. So you always get this, and this c depends on the choice of your weighting function. Okay, so that's this way. So for this choice, you get 1 there. But for other choices that take you between 1 and 0, there are perfectly good ways of regulating some. You get some other numbers. Now, with the sharp transition, this doesn't happen because it's sharp. This is when it's a nice smoother transition. Okay, let me give you another example. of another choice that I want to show you. Let me give you another example of a weighting function. So the weighting function I'm going to choose this time is not this. This is what we had before. I'm just going to throw in a cos. Okay, so this still goes between 1 and 0 with some transition around n. It does a bit of wiggling around a bit, but still, it still goes between 1 and 0. So as far as tau is concerned, and our extension, this is a perfectly good way to sort of regulate the sum. What do you get? You can calculate it. It's very doable. E to the 1 over n, e to the 2 over n, cos 1 over n minus 2 e to the 1 over n plus cos 1 over n divided by e to the 2 over n minus 2 e to the 1 over n cos 1 over n plus 1 squared. Okay, this is what you get, right? So just another way. Right, now, so now we can say, what does this look like? Okay, well, I'm going to show you on a graph. So you can see, this isn't blowing up. This is settling down on a number. What number do you think it is?
Oh, I could hazard a guess.
So you can calculate how this behaves for very large n. So in other words, what does it mean to take n large? It means I'm removing the regulator, I'm removing the cutoff. If I remove the cutoff in this case, I don't get any divergences. I don't get any infinity. I just get minus the 12th, plus the stuff which is vanishingly small as n goes to infinity. This gives you exactly minus the 12th. There's no throwing away of infinity. It really does spit out minus the 12th.
But you've just pulled this out of thin air, this cos n over n. Like you could have reverse engineered that as far as I know.
Well, of course I reverse engineered it.
Yeah.
Right, but the point is, the idea that you always have to throw away an infinity is not true. It depends on your choice of regulator. And in fact, if we go back to this, you can, whatever this c, as I said, it depends on the choice here of the weighting function, the regulator, if you like. And yeah, there are actually infinitely many choices. There are perfectly good regulators, as good as e to the minus 1 over n, as good as a step function actually, that will give you 0 for the divergence. This nice one with the cos is a really beautiful example of it. Okay, so this and all of these, there are an infinite number that will give straight away, they just give you minus a 12 straight out. So who's to say that those are not some sense preferred way to regulate these sums? Is there something interesting in those? So when I...
But you're talking about regulating these sums, putting in cutoff points, right?
And then removing it. I'm removing the regulator because I take n to infinity. I remember, right? You're taking the regulator.
But if you didn't put the regulator in the first place, you would have blown up.
Well, what do you mean? You have to define what you mean by the sum. Okay, and there are ways to define the regulation process that don't give you any divergence at all. And interestingly, this is not analytic continuation, by the way.
It's another method that gives you minus a 12.
But it really gives you it's not like you're throwing away infinity. It's giving you minus a 12. End of story, right? Well, not end of story actually. Not end of story, because there was no way I could sit on this and just think, oh my God, there's all these amazing functions. And by the way, this kind of combination of things smells very string theory-like. It just smells of string theory.
Okay.
And I can't really put my hand on exactly how it is, but it does. Right, so, and also there's something interesting here. So when I first saw this, I was like, this is so cool. This property here, this idea that the way you regulate it, the power law divergence, the quadratic divergence that you see here, that depends on how you regulate it, how you control the sum, and yet there seems to be this universal minus a 12th. That's very reminiscent of something we see in quantum field theory. We see there, we also get power law divergences which depend on how you regulate, how you control well, it's not sums there, it tends to be integrals, which are like continuous sums. And then there's another bit which is universal. So it smells a lot of it, okay? So I started to look more into this. And so my student Robert and I, we started exploring this much more. And we found some really remarkable connection with quantum field theory and potentially string theory that we don't really fully understand. So what do we find? So in quantum field theory, so in physics, so quantum field theory is the theory that sort of describes how basically it's the best theory of fundamental particles that we have, the fundamental fabric of the universe. Okay, it tells you, how the particles are to and fro and how they interact with each other. This is the theory that we use. When you do quantum field theory, you get infinities spitting out. They just come out. There are things like there are infinite sums, but there are also infinite integrals, and you've got to control them, okay, in some way. So you have these control mechanisms to try to do it, and normally you have to throw away an infinity. What we did was we decided to sort of develop a new way of controlling these integrals based on this insight of taus, okay, and applied it to quantum field theory. Then we asked the following question: is there any that are preferred in some way? Now, in quantum field theory and particle physics, the most important thing, the thing that kind of underpins all of particle physics is something called symmetry. So you can think of symmetry as like, reflections, something looks the same. If you look the same under a reflection, then there's kind of reflection symmetry. Or maybe you have a symmetry of rotation, something like a sphere, you rotate it, it looks the same, right? You can extend these ideas to particle physics, and symmetry sort of dictate the structure of fundamental particles and how particle physics works. What's fascinating about this is that usually when you do quantum field theory, when you add quantum corrections to it, you break the symmetries, and that's bad. That sort of means you don't have control of the theory anymore, so you don't want to do that. What we found was that if you use our new way of trying to control the integrals, and we ask the question, when do you not break the symmetries? And it turns out that it's precisely when you use those regulators, those weighting functions, like this one. So it's the ones that give you -1/12 with no divergence, with no infinity, have somehow got something to do with how nature sort of protects us from infinity at the level of particle physics. And we don't understand why this is happening, okay? We wonder if there's something about this sort of the stringy nature of how these interactions are going, how string theory protects us at an even more fundamental level from these infinities. When we've written this paper out that's coming out this week, we're really excited about it. At the moment, we've just pointed out the coincidence that somehow you've got these ways of controlling these infinite sums that gives you -1/12. And somehow they've got something to do with how nature protects us from breaking its symmetries, how it protects us that from happening. And is there something more to be said about it? Maybe there is, maybe there isn't. But it's tempting. When you see these coincidences, it's hard to sort of ignore them. You want to explore them more. And yeah, we're really super excited about it.
Most people in the street, if you ask them about the sum of all the natural numbers to infinity, say, well, it must equal infinity. That's like the intuitive answer. Even Absolutely. You would say that's the intuitive answer. When you have this discussion with someone, you say, well, actually, it could also be -1/12. How do you explain that to them without talking about regularization and string theory and that? What's the one thing you say to them that kind of justifies saying it could be -12?
I mean, I don't think it's possible to explain to somebody in an intuitive sense, because I don't think anybody has an intuitive understanding of it. It's not intuitive. I mean, that's as simple as that. I think the best thing you can say is that, look, this is an infinite sum or an infinite series that, this is what it is. And you don't understand infinity because you live in a finite world and I live in a finite world. We have no intuition for infinity, not really. This goes back, infinity drove Cantor mad. Right? It's not a place that you think you understand, and many mathematicians and physicists have just said stay away from it.
It's almost like you have no right to have an intuition.
Yes, and Feynman, of course, won the Nobel Prize for controlling some of these infinities in particle physics, but he quite openly said we swept them under the rug. Okay, and what we're trying to do is try to find ways to understand. Well, let's not sweep it under the rug. Let's try to understand how the journey to infinity in some sense. Is there a preferred journey to infinity? And I think that's what I would say is happening here, in that you have these ways of taking this sum towards infinity, and there are potentially preferred journeys which take you to a finite place. And we can see that is indeed the case. The system of partial sums, well, that's not going to take you to a finite place. You know this, but that's just one of an infinite class of ways in which you could have carried out that journey, right? And there are an infinite number of journeys that you can take, which will take you directly to minus a 12. And those journeys seem to be special. And I think they're worth exploring in more detail, definitely. People will always think of it as the first bunch of terms, and then they'll try to make that bunch bigger and bigger and bigger. They'll do partial sums, but as Tao has showed us, if you do partial sums, you're doing a very sharp, you're doing a very drastic event, you're doing something very sharp that's actually, you know, it measures zero option in the class of things that you could do. And why are you just because your intuition says do this doesn't mean mathematically you should do that, or even physically that you should do that. And there are these other possibilities, and they give more interesting answers, which maybe are telling us something deep about how the universe works and how numbers work. Process all the way up. And the third one is, of course, going to be our one that we're really interested in, which is 1 plus 2 plus 3 plus 4, and so on. So we're going to evaluate all these three different sums. Now, the first one is really easy to evaluate.
And then you kind of forget. So you kind of put it in a box somewhere, and you put it in a closet, and you kind of you classify it under stuff which you have already understood. But I think actually we don't really fully understand.